Yeah, well, yeah, I didn't have to, I didn't have to pay for socks, but so you push this button and like a pair of, because I have white socks and black socks. So there's two different dispensers now. So you push this button and then a pair of socks pops up like out of a toaster. But they're like folded in this. She told me how they're folded in like, I don't know, it's got like a Swedish guy's name or something like that. The something method. I think it's got like 7 R's in a row, something like that. But yeah, so I have this nice like prepackaged sock that I then have to like unpack from itself because it's like folded in on itself or something like that. Yeah, so that's how I get my socks now out of a machine, and all my shorts in the closet they're rolled up and they're in this like another dispenser thing. But that one you don't push a button, you pull it right out. But it's almost stored like you would store like scrolls. So
Have you seen that thing where people make pictures and they put it on public paper towel dispensers where it just says voice activated, yell paper towel loudly? And then
people start doing it.
Yeah.
Yeah, so that's been the latest entertainment. Every single time she'll say, "Oh, did you notice this?" Like my bathroom, I now have like towers of organizing shelves and stuff. I can't find any of my stuff. You know, I had it just strewn about right where I knew where it was. It's my bathroom. She's got her own. I'm not allowed in the master bathroom. She's got the dual sink. She has like 8 feet of counter space. I'm in the room with the washer and dryer. And I don't even complain. Just stay out. But no, I think she's giving a presentation at this conference. Yeah, I think she's already been doing it for like 2 months, and she's already like, I don't know, brown belt or something like that, and decluttering. All right, so let's take a look. Let me can everybody online hear me?
Yes, sir.
I'm guessing Noah's skipping class.
I am right here.
I expected a C, senor. I got multiples of those last class.
C, senor.
All right, let me hey. It should be sensei. That's true. Downloads. Okay. So homework 6, this is what we were doing, this interior node thingy. So write the following procedures for calculating on a binary tree. This is definition 1.1.7. All right, so this is a binary tree. A binary tree is either just an int or it's a symbol followed by a binary tree followed by a binary tree. So that's your interior node. Okay, so the value of a binary tree is of this guy, your leaf node, is a int. The value of a interior node, I'm assuming they want to be a symbol. So let's see how far the rabbit hole goes here. All right, write the following procedures for calculating on this.
We can't see your screen, Professor.
Well, why not?
Hey, I don't know.
I don't have the answer to that. How about now?
Yep, we can see it now. Thank you.
Okay. This is the definition I just put up there. So binary tree is either it has production int or it has the interior node production, which is a symbol followed by a binary tree followed by a binary tree. So this is a list containing 3 things. So it's either just a integer or it's a 3 list containing a symbol, a bin tree, and a bid tree. Okay, so what are we writing we're writing leaf and interior node, which build binary trees. Okay, let's start with those. Big enough? All right, so we'll define leaf. These are constructors, right? So leaf will be a lambda that takes in a number and boils down to just that number. That's a leaf node. Define interior node to be a lambda that's going to take in a symbol, a elson and an arson for the left and right children, and it's going to return a list, symbol, elson, arson, like that. So that's how we build an interior node. So far, so good. Okay, then we have leaf predicate, which tests whether something's a leaf. Okay.
You misspelt symbol in the list for symbol, elson, and arson.
Yeah,
Look at Clancy.
he's like on his toes. He's probably like he's taking antacids every single day. Like Lippman's just always giving me a hard time. Thank you, Clancy.
I had to catch it before I caught the wrath.
It's true. All right, so we're going to return number on bintree. So it's a leaf if this binary tree you pass it is a number, right? Okay. Next, we have getters now, right? So we have a getter for elson, arson, and contents of, which extract the components of a node. Contents of should work on both leaves and interior node. Okay. So let's start with define elson be a lambda that takes in a bintree, and it should return the binary, or it should return the left son of a binary tree that is in this format. So that's the cadr, C-A-D-R. Then define arson be a lambda that takes in a bintree, and it should return the CADDR of bintree. And then contents of should be a lambda that takes in a bintree. Now this guy, the bintree, can be one of two things, so we can write the test in terms of our leaf predicate, right? Okay, so if leaf bintree, then just boil down to bintree, else boil down to car of bintree, the symbol. So contents of operates on both of these. So the value, so elson, arson are the left and right child, left son and right son, left and right child of your binary tree. The contents of this production would be the symbol, the car of that guy. The contents of this leaf would just be the value itself. Okay. All right, I think that's 1.31. That look right. Go ahead. No, no, I think that's reasonable. Because, but then your predicate would be different. Yeah, which is fine. Yeah, what she's saying is what if instead of a leaf just being a number, you actually constructed a list containing leaf and then that number? Something along those lines? Yeah, and then you use that to say if the car of the list is leaf, it's a leaf. Yeah, no, that's fine. I'm gonna leave it the way I had it. All right, so let's create a binary tree here. So def tree one, it's not def, it's define tree one to be a interior node containing an A and containing a leaf 5 and an interior node containing a B and a leaf 6 and a leaf 7. That should give us a functioning tree using our predicates. So there's our A, left sun is 5, right sun is a list that has a symbol and a left and right sun. So constructors seem to do what they should be doing. If I call leaf on tree 1, I should get a false. If I say contents of on tree 1, I should get the A. If I call contents of on the LSON of tree 1, I should get the 5. Contents of on the RSON of tree 1 should give me the B. Contents of on the RSON of tree 1, and then calling it the LSON of that guy should give me the 6. So on and so forth. All right, so it looks like my getters are working, my leaf is working. Okay, so I think that's the first question. All right, next one. 132, write a procedure called double tree that takes a binary tree as represented in definition, blah, 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 and produces another binary tree like the original, but with all the integers in the leaves doubled. Okay, so it's called double tree. So we will define double tree to be a lambda that's going to take in a binary tree as a parameter. We're going to walk through this tree, and whenever we have a leaf, we're going to boil down to double that leaf, right? So if leaf bin tree, then, and we'll actually be thorough, we'll actually use our leaf constructor to build a new leaf that is the contents of, and the reason we want to actually use these getters is in case we change the definition of how our trees actually are internally stored. Even though we right now know, okay, well, if it's a leaf, it's just a number already, we'll just multiply it by 2 and move on with life. But I'm going to actually use our constructors and our getters and things like that. So if it's a leaf, we're going to create a new leaf that is the contents of our binary tree multiplied by 2. All right, so that's what we do if we're looking at a leaf. If we're not looking at a leaf, what do we boil down to? We boil down to a interior node with the contents of bintree and doubletree on the elson of bintree and doubletree on the arson of bintree. There's our 10, 12, 14. Does that look like doubletree? Okie dokie. And then we should just leave the next one as an exercise for the reader. This was the hard one. Next, okay. Well, that's why this book is so easy to read. What's this?
It was like harder to understand.
All right. Let's make sure the next aligned. Okay, we're ready. What? Was it a good one? Okay, so write a procedure. Mark leaves with red depth. Oh, that's a long name. I should go and create that function here real quick while it's still fresh in my mind. Define mark leaves with red depth. All right. Okay, it's going to be a lambda that I'm assuming is taking in a bintree. Produces a binary tree of the same shape. Okay, so basically it's the same binary tree, but with certain things replaced, I'm assuming, as the original, except that in the new tree, each leaf contains the integer of nodes between it and the root that contains the symbol red. Let's see. Except in the new tree, each leaf contains the integer of nodes between it and the root that contains the symbol red. Okay, so if this was my tree and I had an interior node that was red, my leaf, so we have red, we have bar, we've had one red up to this point in time, so both of these leaves should be 1, 1, 1. Now we have a second red, so this leaf should be a 2, and both of these guys should be 2. So it's the number of reds we've bumped into. Okay, so as I walk through this tree, I have a red. So 0 is now a 1. I hit an interior node. Do I have another red? Nope. So still a 1. I hit a leaf. What do I do with leaves? I replace the leaf with the number of reds I've bumped into at this point, which is 1. And I replace this leaf with a 1. So leaves become your red count. Okay? Then when I hop back to this one, we have, now keep in mind, this is another call to your, well, actually this would be the arson of my original, arson of my original guy. So you could have a situation where if you had another red in here, both of these would be 2, but when you went and dealt with this one, it would still be 1 because it has only seen 1 red. Go ahead.
So, like the way this was worded, the one like is just the top red the root, or like are each of binary trees that have their respective?
Well, yeah. So this is the root here of this whole tree. This is the root of this subtree. This is the root of this subtree, which has in it another root of this subtree. Yeah. So if this bar also said red, then what we'd have here is we'd have red bar 2, 2. Then we bounce out of there. We're back to it being 1, but then we hit 2 again. So now it's 2 again here. So it's only, so if this bar here, if this was red, it's 2 as long as we're still inside this tree. It's the number of reds you bumped into between where that leaf is and the root of the tree. You and the root. Okay, so we need to be able to keep track of the number of reds here. So we're going to need a helper. So helper will take in a lambda. They'll take in a binary tree and a count. And then what this guy will return is my helper passing it the bin tree and then initially at a 0. All right, so my helper, I have a current count. So now what I want to do is if I am looking at so we're building, well, we're building trees, right? But we're replacing the left and the right sun as long as they're leaves with counts. That make sense? All right, so we'll go ahead and we'll put a cond in here in case I have some extra things I want to say. So if leaf, bin tree, then what are we going to do? We're going to boil down to count. That's the number of reds we've seen up to that point. All right, if it's not a leaf, it must be an interior node. If it's an interior node, what do? Well, we build interior nodes out of, so we're going to go ahead and, so I guess I didn't need a con, but that's fine. So we'll say interior node, and this guy is going to be built using the symbol, what do we call that, contents of my bin tree, along with the mark leaves with red depth helper. But what I'm going to have related to that is going to be either the current value or 1 greater if it's red. So actually what I can do here is the cond is going to be helpful. So I'll do it this way. So if I'm in this section, I know that I'm dealing with an interior node. So I can say if equal contents of bin tree is red. If that's what I'm looking at, then I want to create a new interior node with the contents of bin tree along with mark leaves with depth helper passing it the LSON of bin tree along with the plus count 1. And the RSON of bin tree with count plus 1. Else count will stay the same. Yeah, so I always put I have my helpers, and then I just make the original call to helper with the right starting value. Okay, so we need to give ourselves a sample tree to work with that matches our red stuff. So we have red bar 2612. Let's just define a new tree. Define tree 2 to be an interior node, red, whose left guy is an interior node, bar, who's a leaf, 26, leaf 12. And then whose right is an interior node, red. Whose left is a leaf 11. And whose right is an interior node, QUUX. Left is 117. Right is 14. Now we should be able to call this guy on tree 2. Get our red bar 1 1, red 2, blah blah blah. That look right?
In the problem, why is it phrased as like the node between red and the blue? That got me confused.
Yeah, I get what you're saying.
I thought I was supposed to have like bars and that level.
Produces a bin tree of the same shape as the original, except that in the new tree, each leaf contains the integer of nodes between it and the root that contain the symbol red. The number of ones that have the symbol red. But I mean, I get what you're saying is like it all streams together. Like they probably could have explained it with I mean, the example is reasonable enough, I guess, but they probably could have given an example that sort of, like this example is kind of an easy example because it doesn't handle the situation where you have a subtree that has a number of reds that's different. Like maybe the LSON has a different number of reds than the RSON. So you lose a count through the recursion, which is correct, but they don't really give you that as an example. So I could see potentially implementing it with some sort of like, you know, from coming from a traditional programmer's perspective, one thing that you're probably all kind of suffering with right now as you go through these is you feel like you really want to have a global variable like a counter. Like that would be like really good if I could just kind of like pop something up there, just kind of, I'm going to increment that number. I'm going to use it later. It's going to be fine instead of this mentality of having to kind of pass it along. Because you probably come into these problems and that's almost like your initial go-to move for thinking about it, you know, you kind of know you got to pass the count along and you're trying to figure out maybe the trick, but your go-to move is this this bigger thing or this older style thing that you've been used to doing for the last several years. I can see how then when you just have stuff given to you almost like in word problem format. Maybe I've told this to classes before. Did I tell you about I used to be terrible at word problems in math because I wouldn't pay attention long enough. And so like it was in high school, like an algebra class or something like that. It was a word problem that, you know, talked about fruit or something like that. Like you have so many apples and so many pears, something like that. I don't even know what I was thinking. I gave my answer in terms of oranges. I had the right answer, but the wrong fruit. And it wasn't even one of the fruits to choose from. So my dad went, yeah, see, they used to do things. My dad went in and yelled at me in front of the teacher. I wish people would do that today. Have a parent march their kid into my class and just start screaming at him in front of the teacher. Actually, it always worked that way. Because when I was in first grade, I was as you might imagine, I was a discipline problem. And so they used to be able to spank kids in school. So I got beat 3 times in first grade. One of them was for eating crayons. That shouldn't have counted. True story. All these are true stories. I even remember the moves. You come out of the room, you turn right, you go about 30 feet down the hall. There's a little door on the left with a single light bulb. And then she had her weapon hanging on the door. Mrs. Mullinex. Years later, I ran into her at a chiropractor. I was significantly larger than her then. But, huh?
She didn't try to beat you.
Right. My parents loved her. He's like, you straighten Michael out. Something along those lines. But what I was getting at with that is, so after I got in trouble at school, and the teacher hit me at school, then they call your parent in, and your parent stands there while the teacher yells at you again. And now you know what's wrong with me. That's how it went down. Yeah, but the punchline here for your long story short is this kind of reads like a word problem, so I can kind of see how it kind of throws you in circles, even though if you read it with the right cadence, it makes sense. But when you're just trying to read it and it's just a blob of stuff together, I could see where it'd be confusing. So yeah, this one is not hard if you read it the right way, but I can certainly see that it would have been difficult just because of the way it was worded. All right, but does this make sense? Okay, so I think that's what's most important. Let's go that route. Let me, oh, it's a lot of stuff. So I'll put this on Slack. So you have those values. Okay, and we've been talking about variable environments, okay? Occurs free, occurs bound, we kind of got that. We talked about last time we wrote a variable environment, right? We wrote it in terms of those constructors. So we had an extend env and we had an empty env, and that gives us the flexibility. Because one thing I do expect in this assignment when I go and look at them is, my guess is if you got past kind of the wording issues, many of you probably treated your tree in here the way that you knew your tree was already developed, not using the constructors and stuff you just built. So there's kind of 2 disconnects there. So you see here, I'm using leaf to build a leaf. I'm using interior node to build an interior node. I'm using contents of to get the value. I'm using, you know, LSON to get the value, RSON to get the value. I'm not using catters and cadatters and things like that, even though you know you can. The whole idea is, why did we create these constructors and these getters? What's the purpose of them? The perfect purpose of them is for us to describe a data type in terms of its constructors and its getters, let's say, so that later on we could potentially change our data type, update those constructors and getters, and then not have to change functions that we've written to operate on that data type. Contents of internally works differently, but it still gets the contents of it. Building a node internally might work differently, but you know, see what I'm getting at? So it's kind of the joke and then the punchline. Why did we write these things? We wrote these things so that we can conveniently create and work with the binary tree data type, which potentially could change in the future. You know, we already kind of talked about how our environment data type that we're working on could also change, right? Because we're already seeing that we sort of kind of, at the very least, have a weak scope, right? We can have two variables named S that have two different values, and as long as we're, don't have recursive scopes where maybe we've called two separate functions that both are operating from the same starting scope, but then change the value in their own scope. These guys now have different values, but our current environment might not necessarily handle that appropriately because we don't have a way of leaving it once we bounce back up a scope. So basically, we don't have a data structure for that even considers scopes right now. They're kind of handled by luck. Whatever was our most recent redefinition of a variable, that's the one we'll find when we call apply env. All right. Oh, this has to be going up to big integer. Oh my gosh, that one's a nightmare, and that's over the weekend too, Clancy.
Oh, please.
Oh, man, you thought this assignment was bad. Even the name reads funny. It's called Bigot. Yeah. Like what? Oh, you're right. I think it's supposed to stand for big integers, but I feel like I could have named that better at the end of the day. All right, so we'll do something similar to what we did last class in preparation for this. But here, why don't I give you a little bit of the punchline first so that you can kind of see where I'm taking you leading up to that. So we have this idea of a big num representation. Now let's put this in context. So before we go and read the stupid paragraph, what are we really trying to do? Normal computer science stuff, right? I have a big number I want to represent. We prefer to represent it in hexadecimal, base 16, something like that, because it has a smaller footprint, right? All right, so this example says, in the big num representation, numbers are represented in base n. If n is 16, it's base 16. If n is 24, it's base 24, yada, yada, yada. For some large integers n, the representation becomes a list consisting of numbers between 0 and n minus 1, sometimes called, I think it's supposed to be bidgets. Like instead of digits, it's bidgets. I think that's how you're supposed to pronounce it. I don't know where your mind was going there, Rocker, but, let's keep the class. What did I say?
There's no class in 470.
That's true. That is true. All right, so sometimes called bidgets rather than digits. This representation makes it easy to represent integers that are much larger than can be represented in a machine word. For our first, so they say represent as machine word and representing big numbers and smaller footprints. Let's see. For our purpose, it is convenient to keep the list with least significant digits first. So it's actually kind of in reverse to what we, because we're constructing a list, and we usually think about when we build like a hexadecimal value, we start from right and move to the left. But since we're consing a list, I think they ended up building it backwards, but let's confirm that as we go through there. One thing you'll notice though is I do not think this definition has you map from like, a 10 is an A, a B, because you actually have the individual, like the car of the list would be an 11, right? You get the whole 11. You don't have to deal with just the one character. So you don't actually have to map it to the hextet. You can deal with a numerical value between 0 and n minus 1. All right, so they're saying that if n is 0, you just have the empty list. Otherwise, well, they're defining what's the range of n. So for us, we're thinking n is your base. Could be base 2, could be base 3, so on and so forth. So if n is 16, then the number 33 would be a 1 followed by a 2. So this is 2, actually it is, yeah, it is reversed, like I said. So this is a 1 in the ones place and a 2 in the 16s place. 2 times 16 is 32 plus 1 is 33. So this is the hexadecimal number 21, which represents the decimal number 33. That makes sense? So we are building it in reverse because of how lists work. So this is a 2 in the, well, I'm going to read it this way. This is a 1 in the ones place, a 2 in the 16s place. For 258, this is a 2 in the ones place, a 0 in the 16s place, a 1 in the, what is it, 256 place? 16 times 16. Nailed it. Then it's the 4096 place after that, right? Huh?
What's next?
16,000. No. 32,768. Oh, 65 heads. Signed. I did signed. Where were you on that one, Clancy? Huh. All right, so in any case, we use, this is a digit representation of a number, base 10, and we are converting that. So we're effectively writing decimal to base, where n is the base. So if n was 16, converting a 33 would give you the digit representation 1, 2 as a list. This is a 1 in the ones place, a 2 in the 16s place. Make sense? Okay, so that's the target that we're writing for our homework. All right, now I'm going to give you some stuff that's going to help you write that. Because right now your mind is probably jumping back to, oh, I've done this in Java, I've done this in Python, thinking about the ways you've maybe kind of accomplished this. But we're going to do this in terms of a simpler, the idea of a successor and a predecessor. What comes next? And we're going to see kind of how that works. Well, I want to see if I want to give this to you, though. Oh my gosh, that's the worst thing ever. Well, it's actually 2 3-star problems. Oh no! All right, let's here, let me go backwards here. Let me start with this, and we will, since I've already explained the bidgets, we'll do the bidgets for homework, and then after we explain this successor predecessor thing, we'll go back and we'll write this as a team. How does that sound?
That sounds awesome.
No, except you, Clancy. I'm kicking you off right now. You got to do 1, 3, 4, 1, 3, 5, and bidgets. Let's do them all.
I expected nothing less.
How are you recovering from your lift?
Oh, I'm good now, but doing deadlifts so close to squats was definitely not a good idea. That was not fun.
All right. So we have this idea of an well, we've been talking about abstract data types, trying to get our mind to start shifting in that direction where it's an uncomfortable place right now. But in this thing, we've defined a couple of different starting points. So we have this idea of a base that's 0. 0, 0, right? 0 is the same number, so this is kind of a hint towards the bidget thing. So 0 in base 2 is the same as 0 in base 3 is the same as 0 in base 4, yada, yada, yada. All right, so we have a baseline of 0. And we have a way of asking, is this 0? We can always ask if a value is 0, correct? Okay, so pretty self-explanatory. If it's 0, it's true that it's 0. If it's not 0, it's false that it's 0. Okay. Now, if you have a 0, what's the successor of 0? What comes after 0? What's next after 0? You go 0 and then 1. What comes after 1? 2. Okay, so the successor of 0 is 1. The successor of the successor of 0 is 2. The successor of the successor of the successor of 0 is 3. See where this is going? All right, so that is a recursively defined data type. If I need the next one, what do? I call the successor on it. That gets me the next one. Make some sense? Similarly, predecessor says, what's the predecessor of 2? The predecessor of 2 is 1. Predecessor of the predecessor of 2 is 0, so on and so forth. Okay. Make sense? So now it's a matter of how do you describe values as you're counting up. Okay, so if you think about this in the Bidget world, when you're in that first place, what are the possible values that can be in the ones place of a n equals 16 Bidget? We're talking about hexadecimal now. So if I'm looking at the ones place in the hexadecimal number, what are the possible numerical values that can be there? 0 to 15. You know, so in our world, it's 0 through 9, A through F, but in the Bidget world, they're letting us use full numerical values because we have lists that we can store the whole thing, so that's convenient, right? So 0 to 15, 0 to n minus 1. Because if we had a 16, that means it went in another time. And if it went in another time, what does that mean? We should be on the next element of our, we need to get the successor of the next thing. So the successor of 14 is 15. The successor of 15 is 0, 1. Okay, so I have the list. The list has just, we're only in the ones place right now. It goes from 0 to 1 to 2 to 3 to 4 to 15. The successor of 15, if I'm dealing with base 16, the successor of 15 is the list 0, 1. 0 in the ones place, 1 in the 16s place. That's a 16. The successor of 16 is 1, 1. The successor of that is 2, 1, 3, 1, 4, 1, 15, 1, 0, 2. 1, 2, 2, 2, 3, 2, 15, 2, 0, 3. Get how successor is going to work with Bidgets? Huh? Correct. Correct. We're just counting. And if something hits that 15, what does it mean to do? Get it to 0, bump up the next number.
Is this like really inefficient though?
Well, okay, so the question is whether it's inefficient. I think the answer is clearly yes, it's inefficient, but it's abstractly defined. We don't have to do, oh, this is the ones place, the twos place, the threes place. All we have to do is have these two abstract concepts of successor and predecessor and 0, right? That's all we have to have. I could say, what comes after 15? 0, 1. The highest I can get in one column is 15. So once I go up from there, that becomes a 0, and now I have a new column. And that's a 1, and that goes to a 2 and a 3 as this guy keeps hitting 15, hitting 15, hitting 15, hitting 15. We count up as soon as this guy hits 15, then I get a third column, right? 0, 0, 1. So on and so forth. And that's all done in terms of this concept of successor. So yes, inefficient, but also simple in its definition. Okay, so when you go to do the Bidget problem, you're going to be thinking about it through the lens of what is the next value? What's the value after that? What's the value after that? Instead of thinking it from an iterative loop perspective. That make sense? Okay, and that's why they have you do it in the list format, because when you do hit a 15, you're going to be now consing a 0 onto this new vertical that you're going to be building up. Then once that hits 15, you'll be consing a 0, 0 onto this new vertical that's you're building up. The 1's place, the 16's place, the 256 place. But all those is the first bucket, the second bucket, the third bucket of your list. Make some sense? All right, so you'll be implementing Bidgets in terms of those. And then, this guy gives you some examples of like, what's plus. Plus is the successor. I already kind of said this out loud, So the successor of 0, so depending on what plus is, if you want to add something to something else, you have to call successor some number of times. So 2 plus 3 is the successor of 2 plus the successor of the successor of the successor of 2. You call successor recursively 3 times to add 3 to it. Make sense? So here's a definition of the function plus built in terms of successor. Okay, so those are your primitives that you'll be working with for solving this big num representation. So your homework for next time, what was this one? Homework 6. So we'll say your homework for next time is homework 7. But let's go back and look at this guy as an in-class. Okay, so exercise 134. 3 stars, Clancy. Oy. Oy.
No good.
What's up?
That's no good, senor.
Oh, especially since I have to read the paragraph. I might give my answer in terms of oranges. That's no bueno. All right, Noah? Si, senor.
Si, senor.
All right. So write a procedure called path that takes an integer n and a binary search tree. Okay. Now we need to go and look. Binary search tree is different than a binary tree. So binary search trees are going to play by, I'm presuming, play by the rules of what we consider to be a binary tree, where everything to the left is less than or equal to, everything to the right is greater than. All right. So we'll go and look at that on page 10 in a minute. That contains the, let's see, in a binary search tree that contains the integer n and returns a list of lefts and rights showing how to find the node containing n. GPS directions, right? We're going to walk our tree giving the series of lefts and rights to get us to our destination. All right, so for example, if I was looking for a 17 here, and my tree looks like this. Well, I'm looking at a 14 first. Now, even though this guy looks a little bit crazy, I think this is the entire left sun, and this is the entire right sun. Yep. So all these numbers are less than the 14. All right, so we'll go to the right sun there. So we're looking for a 17. The first thing I look at, the value here is a 14. Should 17 come to the left or to the right of a 14? 17 is greater than 14, right? So I need to go to the right. It's not, well, first of all, it's not the number I'm looking for. Okay, so then we ask, where is the number I'm looking for? Is it to the left or is it to the right? It's to the right. So I'm going to record and I'm going to move to the right first. I'm giving myself GPS directions. Take a right, go to the right sun. So now I'm going to deal with the right sun down here. Left sun I've blown past. I know if 17's there, I know it's not up here. Make sense? So now I'm looking at a 26. Should a 17 be to the left? Well, is a 26 equal to 17? No. Should a 17, is it less than 26 or is it greater than 26? Less than. So if it's going to be found, it's going to be in the left son. Left. So we'll look at the left son of this guy, which is this guy right here. I'm looking at a 20. Is a 20 the number I'm looking for? No, I'm looking for 17. So is a 17 to the left or to the right of a 20? Left. Left. So now I'm going to go to that guy's left tree. Did I find my answer? I did. Here's the GPS directions to get there. Right, left, left. And they're representing leaves as the empty list. So the left tree of this 7 is the empty list. The right subtree is the list that has a 12, whose left tree is the empty list, whose right tree is the empty list. Left and right sons are null. All right, so kind of understand the problem we're trying to solve here. It doesn't seem like it should be a 3-star question. It's a 2.25. All right, so the procedure is called path. The hardest part is going to be writing our example binary search tree. So let's write that first. Let me look at the second one and make sure the second one's not going to. Yeah, we're going to rate our constructors. That's what we're practicing, right? So with that in mind, I'm just going to redefine. So a leaf here is going to actually take in nothing and boil down to the empty list. That's how we build a leaf in a binary search tree, right? The leaf nodes are the empty list. An interior node now has a number, an LSON and a RightSON. So we'll have our number, LSON, and RightSON. So changed a little bit, but not the end of the world. All right, asking whether something is a leaf. We're just asking whether it is null bin tree. That'll be true if it's a leaf. How do we get the LSON from a bin tree? Well, we'll get it the catter of the bin tree. Same thing we did before. That we didn't have to change that at all. RSON, same thing as we did before. No problem. Contents of a bin tree. Well, if it's a leaf, the contents of, we maybe can even make the argument that contents of doesn't make sense for a leaf because a leaf is an empty tree. But we'll just return bin tree. It'll give me a null. That's fine. And then the contents of a interior node will be the car of it, which is going to be in this case a number, right? Now, we're not even talking about how trees are put together. We can build a whole constructor type thing here to make sure when we start adding things to our tree, it drops to the correct left or right subtrees. But we're going to hard code our nodes here. So we're going to call this guy binary search tree 1. Let me get rid of these other stuff. I already put it up on. I already put it on Slack, so it's preserved. So we're going to represent this tree here. So I need a interior node that's 17. So interior node 17, whose left son is an interior node that's 7. Whose left son is a leaf. Yeah, actually the constructor for leaf here doesn't actually take anything. Oh, sorry. Yeah, constructor for leaf takes nothing. So I'll have my leaf there. And just want to double check that. Takes in nothing, returns the empty list. Great. So 7, left child is the empty list, right child is an interior node 12. Whose left child is the empty, whose right child is the empty. Leaf, leaf. All right, So that is that part of it. I'm gonna kick this down a line. So that's its left sun. Its right sun will be an interior node. That is 26. Whose left sun is an interior node 20. Whose left sun is an interior node 17. Whose left and right are leafs. Whose right is a leaf. And whose right is an interior node. That is a 31. Whose left and right are leafs. All right. So that's our binary search tree. Let's just make sure that guy. Yeah, I think it looks right. Okay, what time are we out of here? 25? All right, we got plenty of time to do both of these. All right. So defined path is a lambda that's going to take in a binary search tree. So we'll name it as such. That gives us some definition of what it is. And we're going to start where our answer is going to be generating a list. Okay. So we're going to have a, I'll do a cond. All right. So we have a test to see if we're looking at a leaf. If we're looking at a leaf, that's definitely not our answer, right? So if I'm looking at a leaf, that means I've run out of places to check. So I'm just going to return the empty list, right? So leaf binary search tree, I can boil down to the binary search tree, or I'm just going to be more specific and I'll end my conses. I've run out of stuff. We didn't find it. Did it specify what we should do if we couldn't find it? Oh, if n is found at the root, it returns the empty list. That's just if we found it at the very beginning. That's fine. It's going to work out on its own. It doesn't really tell us what to do if we didn't find it. Yeah. So I mean, I think that if we're going to give full directions, and it might just end at a dead end. So I think that's how it's portrayed here. All right. So if I'm looking at a leaf, I have nothing to look at. And again, this is a good pattern to kind of pay attention to, because as you're writing these, my guess is still, as you're working at these in a group and things like that, you're still trying to envision the whole problem at once, rather than think about it as, this is the grammar I'm working through. Right now, we're working with this production. What does it mean to give the path for this one production? If I'm looking at the leaf, the empty list, the answer to what is the path is the empty list. I don't have to worry that this is one little part of the larger solution. I'm answering the one question that's put in front of me. What's the path of the empty list? Okay. So if it's not a leaf, it must be an interior node. But now I'm interested in whether or not it's the node that I cared about, right? So if I want to get the contents of, so if I could actually, since it's numeric, I can use the equal sign. So if equals contents of, and we need to take in a search value here, right? Is that what they called it? Well, whatever, I'll call it search val. So if contents of binary search tree is equal to our search val, if I found a match, that means I've arrived at my destination. I no longer need to take a left or right turn. I'm done, boil down to the empty list, because I know I'm completing a cons, right? Okay. Otherwise, if I'm not looking at the right answer, I need to find out, well, actually, not even otherwise yet. I need to find out, is it less than it? Less than search val contents of binary search tree. If it's less than, then I know it's going to be to the left. So I will cons left onto path of else on binary search tree and the same search val. Right? Else, I'll cons, I'll just write it, right onto the path of our son binary search tree and the search val. And where were you on this one, Clancy? When I defined my tree, the first number was actually a 14, not a 17. So we're going to call path looking for a 17 on BST1. Car expects a pair. Contents of BST search val. Let me make sure my contents of is written right. So if it's a leaf, return the bin tree. Otherwise, it must be a interior node. So I'll return the car of that guy. That looks right. So if this is a leaf, turn that. If it's, let me try calling contents of on my BST1. That should give me a 14 initially. Okay. Then I'll call contents on the else on of BST. That should give me a 7. Seems to work. So arson will get me this. Then else on. Else on of the else on of the arson gives me the 17. Okay, I think contents of works. So now we can look at our path and see where it's going wrong. It's fine if the contents of my binary search tree. So if it's not a leaf, it must be a interior node, which does have a car. So contents of should return that. That should be good. And if it's equal to the search val, we'll return the empty list. Otherwise, if the search val is less than the contents of binary search tree, we're not handling if we don't have. Elson and arson could be leafs. We're just assuming they're, well, actually, no, we are handling that. We are handling that. If it's less than, we'll call will cons left onto calling path on else on, which might be a leaf. Nothing wrong with that. And that same search value. Else will cons right onto calling path on arson and the same search value. Let's just look for path BST1 and 14. That should give us the empty list. Does. Then let's look for a 7. So that should give me just a left. Then let's look for a 12. Left, right. Let's look for a 26th. Is it our second jump? I know we're out of time. It's going to be another 30 seconds on this. Yeah, then it's going right.
We do the when you wrote path and then the number of the list group block.
Oh. When was that?
Just maybe when you called path. Yeah.
Oh. You think I said 17 in BST1? So I wrote it right. I called it wrong? Oh. BST1. Let's see if that's the same error we got. Well, we know what you're doing for homework, Clancy. All right, so we got the code right, just didn't know how to call it. Okay, so homework for Tuesday is the Bidget problem. We'll solve the Bidget problem next class, and we'll also do this other 3-star. And then we will, I think the next thing is we start writing some of our if statements and things like that. Okay, I will see everybody on Tuesday.
Adios, senor.
Later.